Logical reasoning. Under logical reasoning, we'll be looking at simple and compound propositions. What is a proposition? A proposition is a statement or a sentence that is either true or false, but not both. That means it can be true, it can be false, but it cannot be true and false. Now, simple statement is a proposition or a statement containing no connectives. That is, it cannot be broken into subsection. While compound statement or proposition is made up of two or more variables joined together by connectives. Now, these connectives are and, or, if, say A, then B. Also, if and only if. So we basically have 4/5 connectives. Now, logical operators and symbols. For and, that's representation. For or, that's representation. For if, then, that's representation. For if and only if, that's representation. For not, we have three different representation which we can see on the table below. Quickly, we'll be moving to truth table. Now, the truth or falsity of a proposition is its truth value. That is, a proposition that is true has a truth value T, and a proposition that is false has a truth value F. Now, we'll be looking at each logic operators and how we can apply them when solving questions given. Negation, given that P is true, false. Negation P is going to be what? False, true. Okay, so in truth table, there are constant values for or constant representation for your P and your Q, which your P is always TTFF and your Q is always TFTF. So if we continue in this series, you'll see us using this constant representation most times. Now, for conjunction, which is P and Q. P and Q is said to be true if P is true and Q is true. So that means when you are told to find the conjunction, which is P and Q, it is only true when P is true and Q is true. For the disjunction, it is said to be false when P is false and Q is also false. Conditional statement. P conditional Q is said to be false if P is true, then Q is false. Now, for biconditional statement, P biconditional Q is said to be true if P and Q are both true and if P and Q are both false. That's when it's said to be true. If P and Q are both true, also if P and Q are both false. Example, construct the truth table for the following. If not P or not Q, then P and not Q. Now, to solve questions on truth table, you have to solve it as though you are expanding the brackets. So you find it individually, then find one that's in the bracket, then you solve. Okay, so now the first thing you have to do is to put down the constants. That's the P and Q constant. So for P, which you have it as TTFF, and for Q, which you have it as TFTF, we first find not P and not Q. Why? Because they are in the question. So we have to find them individually before you join them together and look for it. So not P will be FFTT and not Q will be FTFT. That's false true, false true. Now, for the first bracket, we have not P or not Q, which implies that it is false when P is false and Q is false. Now, in this case, when not P is false and not Q is false, we have it as FTTT. Now, for the second bracket, we have it as P and not Q, which implies that it is true only when P is true and when not Q is true. Looking at it, we have it as FTFF. Finally, if not P or not Q, then P and not Q implies that the combination will give us false if the first half is true and the second half is false. Okay, so having it as what? True, true, false, false. For tautology and contradiction, When a compound proposition is always true for every combination of values of its constituent statement, it is called tautology. That means after doing everything and you get true, all true. That means it is called tautology. Also, and when a proposition is always false, it is called contradiction. Example, construct truth table to show that P is biconditional to not into bracket not P is a tautology, and P and Q is biconditional to not P or not Q is a contradiction. Solution. Now in this case, I just picked two constant values of P, which is TF. Recall in our P value we have that as TTFF. So I just picked TF to use as experiment. Now I'm looking for not P first, which is what FT. Okay, now I have to look for not P, which is bringing us back to our TF, which is P. Now finally, for P biconditional not P, we have it as what true, which implies that when we have P and not P to be true, or P and not P to be false, the statement is always true. So it is a tautology. Okay, for the second question now, we have to get our P and our Q values, which our P value is what TTFF and our Q value is what TFTF. In this case, we have to look for P and Q first, which is what TFFF. Okay, then we have to look for not P, which is what FFTT. Look for not Q, which is what FTFF. We look for not P or not Q, which is what FTTT. Then the combination gives us what FFFF, which implies that this question is a what contradiction.